last time in our video lecture, we covered the properties of dynamical systems such as linearity, time invariance, system with memory or memoryless systems, systems having infinite or finite dimensionality and causality. Now we will cover the representations of dynamical systems. Okay, I think the first representation that you covered in your school life is ordinary differential equations, ODEs. Okay, so ODEs are very useful and powerful. We can model ODEs. We can use ODEs to model linear time invariant systems, linear time varying systems, nonlinear systems, and of course nonlinear and time varying systems. Okay, so let's clean this. Let's do this. Let's start with the simple case, linear time invariant system. And I think this is basically what you covered in your differential equations class. Okay, so linear time invariant ordinary differential equations has the form such that all of the coefficients should be constant and the y prime and its kind of orders should look in simplest form. There should not be any squares or sines, other kind of nonlinear terms. Okay, so an nth order differential equation has this form: an yn, this is n derivative, a1 y prime plus a0 y. Of course, we have input dynamics such as bn un. It goes like this: b1 u prime plus b0 u. Okay, this is a causal linear time invariant or differential equation representation. Why it's linear? Because all of the coefficients are constant. Okay, all of the y prime, u prime, and basically terms are in its a linear and simple form. There's no, for example, like y prime square term or anything like this. It is causal because the order of input dynamics is equal to the order of the output or variable dynamics. Okay, if this is higher than this, then the system will be non-causal, such as, for example, a derivative operation is non-causal. Okay, but integral is causal. Okay, and in this course, as I told you before, we will only cover causal systems because our goal is designing digital control systems and analyzing digital control systems where plant is an actual physical plant. Okay, so how we can make this linear time varying? So it's a good question. It's very simple. Okay, it's a constant coefficient ODE. If coefficient depend on time, then it becomes linear time varying ordinary differential equation representation, such as ant yn. It goes like this: a0 ty bnt un. It goes like this: b0 tu. Okay, if any of the coefficients varies with time, then this ODE becomes linear time varying system. Okay, so it becomes a representation of a linear time varying system. Okay, it's good. So let's change the slide. Okay, now how we can model nonlinear ODEs. Okay, ODEs. Okay, so for example, let's have an example and let's generalize it. If y prime plus y is equal to u, okay, so this should be y. We know that this is linear time invariant. However, if we make it like this, y prime plus y square is equal to u, it's not linear. So the basic idea is, for a general nth order system, yn, if it's equal to f, is a function yn minus 1, y prime, y, un, u prime, u. This is a nonlinear ordinary differential equation. So the f is a general function. It can be composed of sines, cosines, or any other nonlinear terms. Okay, so we know that we can linearize dynamical systems, which is a powerful tool if we have an equilibrium point or not, but this is a general form, and f is a nonlinear term. As you can see, yn, we leave it as a simple linear term because it can be, for example, square, but still we can just transform it such that the higher order derivative term is alone and singly like this. Okay, this is a nonlinear order differential equation. Actually, it is super easy to write an ODE that is nonlinear and time varying. What we do is we simply clean this and we add a new variable t. Okay, it's very good. So indeed, okay, so this is now a time varying nonlinear order differential equation. We can claim that if your differential equation nonlinear and time varying, we can make it nonlinear and time invariant. How we can do that? We can do it like this. Okay, so if we consider x is equal to t as a state, then it becomes nonlinear, but it becomes time varying because now our state depends on t. So it becomes a nonlinear but time invariant differential equation. Okay, so technically linear time varying and nonlinears can be kind of separated. Nonlinear is a general representation than linear time varying systems. Okay, so these are the order differential equations. And now let's look at what we have in discrete domain. Okay, so for continuous time systems, we have ordinary differential equations. For discrete time systems, we have difference equations. Okay, now instead of derivatives, we have differences. And one of the good things about the discrete time systems is it may be hard to represent discrete time systems in frequency domain. We will use the transforms. But when you go to ODEs and difference equations, understanding difference equations, solving difference equations, simulating difference equations is much easier. So what we do is very simple. If a discrete time system is linear time invariant, we now write the variables in terms of their differences. Okay, this is k plus a n minus 1 y k minus 1 plus a n minus 2 y k minus 2. It goes like this, plus and a0 y k minus n, and we have input dynamics b n u k plus like this b0 u k minus n. Okay, this is a causal linear time invariant difference equation. If you look at the structure, it's very simple. And let's write this. I can write this like this. INYK is equal to minus AN minus 1 YK minus 1. It goes like this, and it until A0 YK minus 1. Okay. Plus B and UK, and it goes like this. Okay. So the idea is, if you know the initial conditions, what you need to do is just look at each variable, like yk minus 1, yk minus n, and use, just multiply them with coefficients, sum them, and you find the output. So numerical or computation solution of difference equations is much easier than ordinary differential equations. In order to find a numerical solution for ODE, you should develop computational differential equations solvers such as Runge-Kutta or Newton-Euler formulations. But solution of difference equations, especially in the computation form, it's very easy. You can just write initial conditions. If you know the input, just you can find the output one by one, like starting from 0, 1, 2, and it goes like this. Okay, so this is causal, as you can see, because yk depends on only its past values of y, current input, and past values of the input. So it's a causal ODE. Okay. However, if I change my equation such that if I write k plus 1 here, then it becomes non-causal. It's also easy to handle non-causal difference equations or systems using the difference equation representation. Okay. It's one of the best things about this. I really like it because I found solving and understanding difference equations much easier for me, and also it's easier to teach the students like you. Okay, this is good. So this is an linear time invariant difference equation. How we can make it time varying? It's very easy. Same thing that we did with ODEs. We will just make the coefficients time varying such that, okay, AK now can depend on discrete time value, YK, It goes like this: a0 k y k minus n. It is equal to, similar to bn k uk, and it goes like this. Now this is linear because all of the y and u terms are in a linear form, but it's time varying because all of the coefficients are changing with time, such that it is linear time varying system. Okay, so this is good. So we made it a linear time varying. How we can make it nonlinear? Very simple. It's the same idea. Now yk depends on a general function f, where the inputs of f is yk minus 1, yk minus 2. It goes like this until yk minus n, uk, it goes like this, uk minus n. Okay, now this is a nonlinear difference equation. Okay, similarly, we can make it nonlinear and time varying. Nonlinear time varying. We need to add k to the inputs of this function. Okay. After ordinary differential equations and difference equations, the most natural and connected representation is the state space. So we covered state space representation roughly at the end of the 3 of the class, but state space representation is very important for control theory and applications. Okay, and I will cover state space very deeply in this course. In continuous time systems, we start with the state definition x of t, which is an element of Rm. Okay, we have an input. If it's single input, it is equal element of R, and output. If it's single output, it's an element of R. Okay, the good thing about state space is it's very easy to cover multi-input and multi-output systems, and techniques, the tools are generally very similar. Okay, so, and then what we need to do is we first define a state evolution equation using the state and input variables, such that x dot of t is equal to A is a matrix, it's a square matrix, x of t plus b u of t. Okay, A is a square matrix and B is a column vector. And we have an output equation, which is y of t is equal to c times x of t plus d times u of t. Okay, and using this representation, we can analyze stability. We can analyze its robustness by converting the transfer function, looking at phase and gain management, and we can design static controllers and Weinberger observers. Okay, so the good thing about state representation is it's kind of easier to extend it to time varying and nonlinear systems, which is similar, and I think it's even easier compared to the differential equations. Okay, so in order to make it time varying, we do a simple trick such that instead of A, B, C, D are constant, they now become a time varying quantities. Okay, so let's clean that. A of t, C of t, E of t, and D of t. Now it is a linear time varying system. By just changing the A, B, and C matrices and making it depend on time, at least one of them, make the system linear time varying. Okay, good. So what about nonlinear? In nonlinear systems, we should change the format a little bit, but the idea is simple. X dot of t should be equal to something which depends on x and u, and y of t still an output equation which will depend on x and u. But since it's a nonlinear system, we can write a general f which depends on x of t, u of t. Okay, and f is a general function. It doesn't need to be linear. It can, for example, composed of sines, cosines, squares, other kind of polynomials, and everything like that. And similarly, output equation, let's call h, depends on x of t, u of t, and since it's a nonlinear system, it's necessarily not nonlinear. Okay, we can still linearize it using Taylor series expression, and we use this linearization technique a lot for computer control applications. Okay, and this is now a nonlinear time invariant system. Making it time varying, it's also very easy. Let's clean this such that we add time as a variable in these equations. Okay, it's very nice. Okay, now this is a nonlinear time varying system. Actually, nonlinear time varying is not very important because if it's nonlinear time varying, we can consider t as a state. And if we consider t as a state, it technically becomes nonlinear and time invariant system. Okay, so time varying concept is important for linear system. So the most important systems is linear time invariant systems, obviously the most important of all of them. Linear time varying systems, and in general, nonlinear systems. If it's nonlinear, it's really not critical to talk about time variance. Okay, good. So this is the state space for continuous time systems. Discrete time systems, the idea is very similar. So what I will do is I will change here and talk about discrete time. Okay, I wanted to keep here. Now this is discrete time system. So instead of depending on t, our state input and output variables depends on a discrete sequence k, right? Okay, so let's clean this. Let's clean this. You can clean that, clean that. Okay, now we use this. Okay, this is un, this is yn. Now we know that n is element of z or z plus. It doesn't matter much. Okay. So you need to define a state evolution equation and similar differential equation. Instead of derivatives, we will use differences, but in the matrix form, such that, okay, x m minus 1 is equal to, no, sorry, it's wrong. Xn is equal to a x m minus 1 plus b u n minus 1, and yn is very similar, exactly the same, xn plus dun. Okay, so if you look at this representation carefully, let's change the color here. Understanding this easier than understanding the state space form in continuous domain, because very simple, x of n, how I can compute it? If you know x in the previous state, just multiply with a, plus if you know the input, b times input, sum it and find the output. So finding numerical solution given a state space solution is super easy. Okay, so output of this equation is very simple. You just start with initial conditions, you just simulate it. Technically it's very simple for loop, forward in time to compute x's and y's. In that respect, state space representation for discrete time systems is super useful because understanding the behavior, finding solutions much easier. In continuous domain, continuous time state space representation, in order to solve the system numerically, you need to use numerical differential equation solvers such as Euler equation or Runge-Kotler equation. Okay, good. So similarly, we can make it time varying such that, okay, so let's clean it. Instead of a, b, c, d constant, they now become depend on discrete time variable n. Now this is linear time varying system. In order to make it nonlinear, we do the same thing such that, okay, so let's clean it. X of n is a function of x of n minus 1, u of n minus 1, and similarly output equation can be nonlinear, h x of n minus 1, u of n minus 1, and this is now a nonlinear time invariant system. Similarly, we can consider n as a state. We can make it linear, nonlinear time varying, or we know that it is already a nonlinear system. Okay, so state representation has this structure for continuous and discrete time systems. Okay, and as I told you before, it's very similar to the ordinary differential representation, but I think it's slightly more powerful and useful than the ODE representation. Okay, good. So let's change it, and now we will move a different representation, which is kind of limited in some sense, but more general in other sense, which is impulse response. Okay, so let's look. Remember our continuous time representation in the impulse response case. Okay, so in continuous time, we know that we can write y of t for linear time invariant systems as a convolution of a function called impulse response and input. For any input, If we can write y of t using this relation, we know that the system is linear time invariant because convolution operation is simply an integral h t minus tau u tau d tau, or similarly minus infinity because we know that it's commutative ut minus tau h tau d tau. Okay, so this representation is specific to linear time invariant systems. Okay, good. So impulse response, as you can see in the original form, is applicable to linear time invariant systems. We cannot model nonlinear systems because the definition of impulse becomes very obsolete. So what is impulse? We know that when u of t is equal to sigma t, we look at the output, y of t is equal to h of t. It's the impulse response of the system. When input is the impulse, your response, h of t, technically characterizes the important features of your system. It's everything restored in this simple function. Okay. However, with a simple modification, we can model linear time varying systems by using time varying impulse response function. Such that in that case, we cannot talk about this convolution operation, but we can talk about a different integral, minus infinity to infinity, okay, u of tau, d tau, but now we have a different function, h, t, comma, tau. Okay, as you can see, in the original impulse response equation in a time varying system, h depends on t and tau, but it's difference. Okay, so we don't need to store t and tau differently, or we don't need to treat them differently. We just look at the difference between t and tau, and h acts like that, and it's our out. But now we need to keep track of t and tau separately, and it seems because of the time variance, your impulse response changes. So your system to impulse at t is equal to 0 can be different, your response, when impulse is t is equal to 10, for example. Okay, so this function can capture this behavior, and we can still talk about impulse response representation, linear time varying systems. In this course, I will not cover this because we will dominantly use linear time invariant models and systems. But this is a nice feature, and it's a powerful feature such that you can extend impulse response for time varying systems. But when you talk about impulse response, it is technically limited to linear systems, time varying or time invariant. Okay, good. So in the mini projects, or especially in the midterms in true-false questions, if I give you impulse response representation, if I ask you whether the system is linear or not, you can just quickly write linear without any hesitation. Okay, so this is the impulse representation in continuous domain. And we know that we have impulse response in discrete domain, and idea is very simpler. Yn now is equal to h of n, and this is the impulse response of the system. But we know that it's impulse Kronecker delta function, u of n. But instead of integral, we have summation minus infinity to infinity h m minus k uk, or similarly minus infinity to infinity u m minus k h k. Okay, so this is impulse response representation. And if you talk about convolution and this form, this is to model linear time invariant systems. Okay, but similar to the continuous case, we can extend it to capture the behavior of linear time varying systems using a different summation, minus infinity to infinity. So okay, like this, h n comma k u of k. Okay, so this is a time varying impulse response function and time varying impulse response representation we can use to model linear time varying systems. Again, we will not use this representation in this course, but we will heavily use this representation to model digital control systems, to talk about the sampling and other kind of features and behaviors. Okay, so similar to the continuous case, if I give you a impulse representation, it is directly linear without any hesitation. If I give you this convolution operation, I say that yn is always equal to this equality. No matter what u is, you can clearly say that the system is linear time invariant. Okay, so our final representation is the most limited one, which is the transfer functions. Okay, so transfer function for continuous time systems is this. So we have a system. This is y of t, this is u of t. If you can write y of s, which is the Laplace transform of y, in the form of this, Then we call this transfer function. As you can see, it simplifies the behavior a lot. In order to find the output, if you know the Laplace transform of u, just simple multiplication, g times u gives the output. This is linear time invariant. So transfer functions are inherently limited to linear time invariant systems. No nonlinear component, no time variant component. There are specific operators, special operators, which are also called like transfer functions, but they're not exact transfer function to model time variant systems. But it is a very different topic. So if I give you a transfer function, I say that it's a transfer function between input and output, you can automatically say that your system is linear time invariant. Okay, so in the discrete time, we have also transfer functions, but instead of S domain, we leave it Z domain such that Y of Z is equal to G of Z, U of Z, where U of Z and Y of Z are the Z transforms of input and output respectively. And this is my transfer function in the discrete domain. Okay, and later we will talk about how we can transform G of S into G of Z when there is sampling and digital analog converter in the control loop. And this will be the core idea when we talk about analyzing digital control systems in a frequency domain. Okay, so that's all that I want to talk about representations. As you remember, we start with ODEs in continuous domain and difference equations in discrete domain. Then we talk about state space representation. Okay, so discrete time and continuous time state representations. But as you can see, compared to difference equations, the similarity was like more concrete. Impulse response, of course, discrete time and continuous time. And finally, transfer functions. Okay, in this case, it was Z domain. In this case, it's S domain. So we have 4 fundamental representations that we will use to analyze and control control systems. Differential equations, difference equations, they're in the same category: state space, impulse response, and transfer functions. Okay, that's all I want to talk about representations. In the upcoming lectures, I will start talking about digital control systems, its main components, and its features.